In this video, we're going to talk about the elliptical shape of orbits and how to measure the eccentricity, or the roundness of those orbits. And typically we start with a piece of paper like this, typically with a center point. In this case it's a push pin. We're going to push it all the way in like that. And if you want to draw a circle, we all pretty much know that you can take the loop of string, bring it out here, and just run it around the center point. All of the points that are a single distance from the center point is the definition of a circle on this plane. But the challenge is that Kepler suggested that we could take a look at the orbit of objects around another object. For example, a comet going around the sun. And if we think about that as being, here's the sun, and an equal distance out here is some mathematical point in space, that instead of having a single center, an elliptical orbit would have two foci. And we can put them in and again just push the push pins all the way in. And now wrap the string around it. And now when we run the pen around the string, it's not circular. It's a type of oval, a special kind of oval, defined by this relationship between the foci, and we call it an ellipse. Now remember that when we look at this ellipse, this is the point of gravity that everything is going around. This is just a point out in space, typically called F or F1, one of the other foci. Now, on the front page of the reference table, it gives us a formula, a really simple one at that, which says if you can measure the distance between the one foci and the other foci, in this case it's 6.0 centimeters, and if we can measure the length of the major axis, think of that as being the biggest of the diameters. Here it's around 12.2 centimeters. And if we divide those two numbers, small one above the big one, we're going to end up with a number less than 1. So we'll grab a calculator, and we get 6 divided by 12.2, and that equals 0.4918, or if we want to round to the thousandths place, that would be 0.492. So we'd say that eccentricity was 0.492. Now that number's, quite a bit smaller than a 1, and all the eccentricities are between 1 and 0. The other thing you can keep in mind is that if you tried to do the eccentricity of an actual circle, remember our original circle, there'd be no distance between the foci because there's only one center to the circle. So you'd have 0 centimeters between the foci, essentially it's one spot, divided by any major axis, and the eccentricity of a circle, whatever it was, would be 0. So a circle is 0. And the farther we push these things apart, the bigger the number becomes. And speaking of numbers, we can always go to our reference table and not only find the formula for eccentricity, but on page 15, we can find a bunch of information the state has given us about planets, including the eccentricity of their orbits. So if we slide down the column, we find, for example, the Earth's orbital eccentricity is so close to a circle, it's almost a 0, but not quite. It is 0.017. So that's a pretty small number. If Earth has an eccentricity of 0.017. That's a much smaller number than the ellipse that we just drew. So we would say that the orbit of the Earth is much more circular, and the orbit that we drew is much more eccentric. One last thing about eccentricities is that once we can draw the ellipse, we can now think about how gravity is going to influence the object. So if you've got a comet going around the sun in this direction, that right here is the sun, and right here is where the object is the closest. So that's the closest it gets. That's also going to be where it has the most gravitational pull from the sun. Opposite over here, we'd have where it is the farthest. And farthest is going to be important because that means that's going to have the least gravity with the sun. So it means that here is not only closest to maximum gravity, but this is where the comet or any object orbiting another object would be going the fastest. And over here is its minimum speed. So all along this part of the course, and the orbit, the thing would be speeding up, and all on this part of the orbit, it would be slowing down. That's pretty much all you need to know about eccentricity and elliptical orbits.